or heat treatment principles. So first topic is mechanical property in steel is influenced by or is affected by. Basically, we already discussed a lot about on this. One is if you remember. Property of the steel will be affected by obviously microstructure of the steel and micro constraints. And we already discussed now what is microstructure, micro constraint, you know that. Like grain size maybe different phases. What are the different phases? What are different micro constraints like perlite, benite or whatever. They will all affect them because each phase have different nature, each micro constraints of different nature. Apart from that also, there is another important point. That is morphology is basically shape or how they appear, and also size, and also volume fraction or relative volume fraction, right? Relative volume fraction of phases. So all will affect the property, right? And we already have discussed how to find out volume fraction, if you remember, by lever rule, right? What are the phases you remember? Room temperature phases, right? Ferrite, perlite, cementite, right? And if it is non-equilibrium, also you know that, benite and martensite, right? Already we have discussed about the nature of phases, right? So all will affect the property, right? The morphology will change, property will change. Morphology means it may be spherical, it may be elongated, it may be little shape, right? So similarly, size may be smaller, may be bigger, right? Similarly, volume fractions may be, if ferrite is less, perlite is more, it becomes more harder. If ferrite is less, cementite is more, it is become more harder and stronger. Similarly, if ferrite is more, but cementite is very less, it is ductile. So, you understood now? So, these are the things which will affect the property of the steel. And all these things can be changed by doing heat treatment. So, we have different heat treatments available to change all these things. Then next is, okay, you remember parent phase and product phases. Which one is parent phase always? Austenite is the parent phase always. Austenite is parent phase. So that is the reason why we always do austenitizing. That means whatever initial microstructure you have in your steel at room temperature, you always heat the steel above to a point where entire structure will be austenite. That means grain and grain boundary is austenite, grain boundary. Okay. And product phase are different product phase you can get. Basically, I am writing in combined forms. Perlite and martensite. This is also mixture of carbide, a mixture of ferrite and carbide. This is the equilibrium phase and these are the non-equilibrium phases. Non-equilibrium phases are always harder and strong, always. And they do not appear in iron carbon phase diagram. People sometimes ask, why martensite and benite is not seen in iron carbon phase diagram? So you can write the answer. How many of you can write? Question is very simple but tricky. Why we cannot see martensite and benite in iron carbon phase diagram? We only see perlite or ferrite or cementite like that. Why? You can simply write because martensite and benite are non-equilibrium microstructures. And iron carbon phase diagram is an equilibrium phase diagram, where equilibrium phases means those phases which form due to very slow rate of cooling. If you start cooling the molten iron or molten steel from high temperature to low temperature in a very slow rate, then only you will get equilibrium structure. But if you quench it You take molten iron and quench it. Quench means suddenly cool it in water or in ice or in any salt solution. Then you end up with martensite or mostly martensite. Benite is something different. We'll discuss that in maybe in coming lecture. You understood? So these are the points. So these are product phases. If you change the product phase, you will change the property. Then next is formation of austenite phase in the steel in hypo-eutectoid and hyper-eutectoid. Okay, fine. So if you see basically, and this is Anderson per light resin. This one. And this is ACA. This is ACA. So this is pro-eutectoid alpha and gamma. Right? So see, that means your parent phase is austenite. Once you cool it, first pro-eutectoid alpha will form, and gamma will form. Right? Then further this pro-eutectoid alpha will remain as pro-eutectoid alpha, no transformation will occur. But whatever gamma will be there, they will transform into perlite or ferrite later on. Anyway, so the thing is, so that means we have three types of steel. No? One is, you can see, eutectoid, one is hypo-eutectoid, one is hyper-eutectoid. These are the three steels we have basically. In eutectoid steel, what is the room temperature phases? Perlite only? Only perlite. That is 100% perlite. That is a mixture of iron and Fe3C. This is the room temperature phase. Now you want to form austenite. So you have to heat it. Where you need to heat it? Just say, you can say above A1. Very good. And you can see that is a fixed point. That is not variable. So to get austenite, heat above A1. That is a fixed point. Or in other way, I can say the initial phase in the eutectoid steel will transform into austenite at a fixed temperature, just above a fixed temperature. That is A1. But in case of hypo and hyper, just see, is this the same? There is a range. Very good. That means this is eutectoid. Fine. You just reach here and you will get austenite completely. But in case of hypo, suppose this is hypo. If you start going to this region, that means initially, what is the phase? I can write here. Hypo-eutectoid steel. So, what is the initial room temperature phase? Ferrite plus perlite. Now you can see, once you start going to this region, above A1, austenite will start forming. But there is not 100% austenite because some pro-eutectoid alpha is still there. right? So that means more you go to high temperature, more nucleation of austenite will form. Finally, the moment you reach above A3, here for example, every proactivated alpha will also transform into austenite. So that means my point is it is a range of temperature. You can write to get austenite heat above A3. To get austenite heat above A3. To get like complete austenite, you can write. To get complete austenite, you have to heat above A3. So I can say range of temperature is available. For austenite formation. And finally, hyper. Same, I can write, okay, room temperature phase is what? What are the room temperature phase? You are saying something. You better write here pro, otherwise you get confused, pro alpha. So this is also since this is proactivated alpha, this side is also you can say proactivated cemented. Okay, so proactivated cemented plus perlite. So again you have a range of temperature. Range of temperature for austenite formation. Well, just see, suppose you are shooting this steel, this is hypereptectoid steel, you just go above A1, you will have two phase region now. Gamma is forming, but still proactivated alpha cementite is there. But the moment you reach above ACM, then you will get all austenite phase. So that means again this is the range of temperature, this is the range of temperature, but for eptectoid steel it is only a fixed point. Got my point? So these are the important points. So you understood why this is happening? Because of proactivated alpha phase present in the hypoeptectoid steel and proactivated cementite present in the hypereptectoid steel. That is the main reason. But in case of eptectoid steel, there is no proactivated phase. Only perlite is there. So it can easily transform into austenite. No issue. Is it right? You understood my point? Now the thing is, your question will be how this is actually what? Solid state phase transformation. There is no liquid formation. Only one solid is becoming and the solid. But what is happening? Crystal structure is changing. Solid state phase transformation is what? Your crystal structure will change. But everything, the parent phase and the product phase will be in solid state. Only crystal structure will change. All the crystal structure is moving towards FCC basically, starting from DCC. Okay, anyways, so the point is how it happens. So basically, solid state phase transformation happens by nucleation and growth mechanism. But there are certain transformations which do not involve nucleation and growth, but most of the phase transformation involve basically nucleation stage, then growth stage. First, a nuclei of product phase will form, and that will grow. That means austenite will form. That means nuclei of austenite will form. It will grow into bigger. Anyway, so the point is, see, suppose I am talking about a perlite. Let it one perlite colony is there. So this is one perlite colony. For example, this is perlite colony. Single perlite colony. This is single perlite colony. Fine. So you can see darker and white regions are there. Alternative darker and white regions are there. Right? Or bright and dark regions. So suppose this darker region you just consider it as a Fe3, and the white region or the bright region you consider it as alpha. Right? Okay. So you can see there is alternate layer of alpha, which is pure iron. Consider it as a pure iron. Alpha is a pure iron basically. Amount of carbon is very less. But cementite amount of carbon is how much? 6.67. Too high. One is pure, one is 6.67. So there is a difference in the concentration, right? And you are hitting the steel. The moment you are hitting the steel below 200, you are not reaching 200 or 200, there will be no diffusion actually. Carbon will not diffuse at all. But the moment you rise the temperature above 200, carbon will start diffusing. Why? Carbon is a very small element, it is very light also, so it can easily diffuse. Lighter element diffuse faster always. So you understand my point? The moment you reach above 200 degrees centigrade, carbon atom will start diffusing out. From where? From cementite. Cementite have high concentration of carbon, ferrite have very low concentration of carbon. So from cementite, carbon will diffuse towards the center. Why? Because you understood. Suppose from this region to this region it will diffuse, and from this region to this region it will diffuse. Okay? Similarly, from cementite it will diffuse towards here, and from cementite it will diffuse towards here, like this. Towards the center. Center is ferrite, both ends are cementite, no? So they will diffuse like this. So, because of diffusion of carbon from cementite to the interface of cementite and ferrite, nucleation of austenite will start. That stage is called nucleation. You can write or you can write. Just the moment you reach above 200 degrees centigrade, diffusion will start. The carbon will diffuse from cementite towards the interface. Interface means the boundary between two phases. That is called interface. Okay. And due to this diffusion of carbon from cementite to the interface of cementite and ferrite, nucleation of austenite will start. Small nuclei will form of austenite. And this will go on. The moment you rise the temperature, more diffusion will happen, right? So that means the carbon from cementite will be depleting with time. No, it will deplete with time, and it will enrich in the austenite phase. Because austenite phase can hold lot of carbon. You remember what is the solubility of carbon in austenite? 2.01 nearly, or 2.1 maximum. But in ferrite, how much? It is only 0.025, right? And cementite is maximum 6.67, too much high, right? Nucleation stage is over. Further nucleation is happening. Further carbon will migrate to the austenite phase, which is nucleated, and finally what will happen? It will grow. Then only everything will become austenite now. So growth will happen in expense of ferrite. So ferrite will get consumed, everything will become austenite now. Nothing will be there, only austenite phase. So finally it will be disappear completely, and you will end up with like this. Some same grain is there, and you may have like this. This is gamma, and this is also gamma. Grain and grain boundary of gamma is there. Same size, same thing. But what is interesting here? Can you tell me? Just imagine. The size of the grain is reduced. The see, small grain size is formed. Gamma is very small. Okay, you got my point. So it occurs by nucleation stage and growth stage. And how nucleation is happening? Because of diffusion of carbon from cementite to the interface. More diffusion, more nucleation, and finally entire ferrite will get consumed by this gamma, and it will become bigger gamma. So gamma will become very big because of consumption of ferrite. This is called growth stage. Nucleation growth stage. But this is actually true for this one, eutectoid. But this may not be true for hypo and hyper. Why? Because of availability of prophages. Now, prophages are also available. So what exactly is happening? Listen carefully. Initial point is same. Because in hypo and hyper also same perlite is there. So nucleation will start, growth will happen. But most of the growth will happen due to expense of protracted ferrite in case of hypo, and growth will happen in case of hyper due to expense of protracted cementite. That is the difference actually. Again I am saying, in case of eutectoid steel, growth of austenite will happen due to expense of ferrite only, ferrite. But in case of hypo, growth will occur due to expense of protracted ferrite phase. And in hyper, it will happen due to expense of protracted cementite phase. That is the difference. Other nucleation is same. Nucleation will always happen due to diffusion of carbon from the cementite to the interface. That is the difference actually. So that means which one is fast and which one is slow, you can say. In eutectoid steel, it will be very fast. Kinetics will be obviously very fast, right? And just understand this point. These pro-eutectoid phases are basically one grain you can consider. Those are actually one. Pro-eutectoid alpha is also one grain. So some nucleation may happen along the grain boundary of the pro-eutectoid alpha phase. Similarly, some nucleation may happen along the pro-eutectoid cementite grain boundaries. So it doesn't mean that all the nucleation will happen in the perlite. some nucleation may happen along the grain boundary of the protected phases. Do you understood now? Right? Because that is also grain boundary, and grain boundary is a high energy region. So nucleation can easily occur. So most of the nucleation always occurs along the grain boundaries, because grain boundaries are high energy. Energy is already available for the nucleation. I mean driving force is available, you can say. Okay. So this is done. Okay, next we'll move to kinetics. So this one is important actually. Kinetics of austenite formation. So you may get questions from this in the end semester or mid, maybe. I'm not sure. Maybe end or mid you can get questions from this. So one is kinetics. Let me erase it. And in gate exam maybe also you can get questions from this part. This is actually important. So kinetics means what exactly? Kinetics means it will tell you how fast austenite will form or how slow austenite will form, right? Because we are transforming our room temperature phase to austenite. So how fast it is happening or how slow it is happening. So we will discuss that. Okay, temperature of the transformation, holding time. Okay. So the point is, we will consider effector speed. So explain it. Okay, to explain it, let me talk to you about this one. It's better. Suppose this is one of the maybe prior austenitic grain. So prior austenitic grain will be what exactly? So nucleation will start from here, right? For example, let it be. Prior austenite, suppose I am talking about cooling now, just imagine, I am cooling. I have parent austenite, that is the prior austenitic grain. The moment you cool it, transformation will start. Okay, so new phase will come out. The new phase will form along the grain boundary, you can see, along the grain boundary, red phases have formed, small red phases. This entire black is the prior austenitic grain, from which new phases transform when cooling. Okay? So this is, you can consider this is grain of perlite. Why? Because I have chosen which steel, effector steel, right? So these are actually grains of perlite. Grain of perlite. Okay. All these red phases are grain of perlite. But what is perlite is colony now. Colony means, so colony basically means like this. What are colonies? Colonies are, so this is one colony. Colony of perlite. So this is again colony of perlite. One colony. So multiple colonies will be there in one grain, that means. And what is the difference between the colonies? If you go from one colony to another colony, the arrangement of ferrite and cementite lamellis will be different in orientation. That is the difference, you have to remember. Otherwise many people get confused. So grain is different, colonies are different. That means each grain of perlite have multiple colonies of perlite, you can say. So suppose, I am giving one example, otherwise you get confused. Suppose I am considering this grain of perlite. So colonies will be maybe like, so this is the orientation of the ferrite cementite. Maybe in this grain, the orientation will be like this. You see, there is a difference in orientation. In this grain, the orientation may be like this. You got the point now? So one grain of perlite is having multiple colonies, and orientation is different. The lamellis orientation is different from one another. You consider, suppose you consider this grain, for example. This grain of, so Suppose orientation is like this in here. Here orientation may be like this. The orientation may be like this, and this may be like this. So one color is 2, 3, 4 color is are there. This is also 1, 2, 3 color is like this. And maybe many people get confused. Suppose I am saying fine perlite and coarse perlite. So fine perlite means the distance between the lamellae will be reduced. Coarse perlite means the distance between the lamellae will be more. It doesn't mean the size of the grain and all, basically. Size of the grain may affect sometimes, but if somebody is asking what is fine perlite and coarse perlite, fine perlite means the lamellae distance will be reduced. There is a small gap between the lamellae. If the lamellae gap will be large, it is called coarse. Do you got the point? Fine perlite means the lamellae gap will be less. Distance between the lamellae gap is less. If the distance between the lamellae gap is more, it is called coarse. So, can you tell me now, suppose I have dislocations in fine perlite and I have dislocation in coarse perlite. Now you are applying load, tensile load. So what will happen? Dislocation will travel, I mean it will slide, or you can say it will glide, technically called gliding of the dislocation. So in which case gliding of dislocation will be easy? Fine or coarse? Coarse, very good. That means coarse, if you still have coarse perlitic structure, it is ductile. If you still have fine perlitic structure, it is stronger, harder. Right? Why? Now the question is why? What? कैसे हिंडर करेगा? Yeah, that is the right actually. Because the spacing is less. So that means, just imagine a situation here. Imagine a situation. I am suppose these red are Fe3C, and this region is alpha, ferrite. Like alternate layer of ferrite and cementite is there in perlite. Okay, first of all, you understood what is actually lamellar spacing. Lamellar spacing means from here, center of the one cementite to center of another cementite distance is called interlamellar spacing. So this is called interlamellar spacing. So interlamellar spacing means center of one cementite to adjacent cementite distance. Many people thought like, some people thought like from here to here. It's not exact. It is from here center to center. Similarly from here to this center. These are adjacent cementite. These are also adjacent cementite. So center of one cementite to adjacent cementite distance is called interlamellar spacing. So that means if somebody will ask furthermore, what you will say? It is containing what? One interlamellar spacing containing what exactly? One full ferrite and one full cementite actually. Just see. Just see and you will understand. Your interlamellar spacing is having one full width of ferrite and one full width of cementite also. Just see. Half, one and one full ferrite. You understood the point? This is very interesting actually. So, if this gap is more, so what do you mean? Your cementite, adjacent cementite distance is more, right? If this distance is less, adjacent cementite distance is close. So suppose you have now a dislocation. One dislocation want to glide. Suppose dislocation is like this, for example, in a ferrite. One dislocation is like this, it wants to glide in this direction or in this direction. Okay? So what will happen? Ferrite is very soft, dislocation is easily moved because it is soft, na ferrite. But cementite is very hard. It is a precipitate, you know that basically. Consider it a precipitate. So it will glide and stop here. Right? Similarly, if you want to glide, it will glide and stop here. So I mean to say, if the perlitic colonies are finer, that means the dislocation will interact more with the phase boundary. More phase boundary is available. Again I am saying, because of presence of more phase boundaries in fine perlitic structure, dislocation cannot move easily. There is a hindrance to the motion of dislocation. Because the moment it will move, it will stop, because and the cementite will come, right? Again, suppose it will cross over, maybe let it be, it will crossing, and it will interact with the cementite suddenly, so it cannot move. So strength will be more, because strength will depend upon the dislocation motion. If dislocation is moving easily, it is ductile. If dislocation movement is hindered, very slow, it is stronger or harder, or whatever you can say. Do you got my point? So you can write, because of presence of what? Lot of interface boundaries in fine perlite structure, strength of fine perlites are actually good or high. Is it okay? I think you understood the point, no? So actually, basically, there are certain heat treatment by which you can produce fine perlite. Also, you can also produce coarse perlite. We will discuss that in coming lecture. Different heat treatments. That's why we are studying this subject now. How you can improve the property. So that means, I told you now, we can change the morphology. So you can change the morphology. You can reduce the lamellae distance. You can increase the lamellae distance. You can produce fine perlite structure. You can produce coarse perlite structure in the same steel, same composition. Everything is same, but you can produce fine and coarse by doing different kind of heat treatment. So basically, I am not going to details. Actually, that is called annealing and normalizing. We will discuss that in coming lecture. Annealing means slow cooling. You can have coarse perlite. When you do normalizing, that is fast cooling. You can have fine perlite. That is the. We will discuss that in coming lecture in detail. I think it is fine. So now the question is, okay. You can see kinetics of austenite formation. So how fast austenite will form or how slow austenite will form, it will depend upon three factors. You can write. Three factors will decide the kinetics of formation of austenite. Three factors. I have already written, you can see what are the three factors. What are the three factors? Can you tell me? It is already written. See the factors affecting formation of kinetics. No? One is the temperature, predetermined temperature. One is the holding time at the predetermined temperature, and finally is the nature of perlite. These are the three things which will decide. So let me draw a diagram quickly again. Anyway, so you can see, so this is room temperature. I am considering perlite here, 100% perlite. So I choose one temperature here. I choose one temperature here. I choose one temperature here. Here and here. Okay, I can choose many temperatures. So this is one temperature, this is another, this is another, this is another temperature, this is another temperature, this is another, and okay. So that I can T1, T2, T3. So you can see T7 is greater than T6, T5, T4. And steel is which steel? That is so I have considered eutectoid steel, but to do austenitizing I have chosen many temperatures. T1 is very less, T7 is maximum. You can see. So you can do this same experiment in your lab also if you want. You can ask sir to do this experiment. It will be very useful for you also. So starting phase is 100% perlite. Now you choose different temperature of transformation or predetermined temperature as we discussed. So you take very small size piece of steel. Why? Because you want to form austenite at a very fast. Holding time will be less, that's why. You fix all the sample dimensions same. That means you need to choose how many samples? 7 number of samples. Same composition. 7 number of samples. Sample dimension is same, small size. Holding time is also same. All are same, right? Composition is same, holding time is same, dimension of the all sample size is same. That dimension is thickness, basically. So you choose 7 different bath where the temperature is of T1, that means one bath will be having T1 temperature and the bath will be having T2. So different bath. Bath means actually salt bath. We call technically it says salt bath. Molten salt will be taken as a bath and it will maintain a particular temperature. Right. You can do same thing in the furnace also. But what is the difference? Furnace don't have uniform temperature. Right. That is the reason. But if you take salt bath, molten salt bath, everywhere temperature will be same. So that's why we choose, most of the experiments are done in salt bath furnaces. We have one salt bath furnace in mineral processing lab. You can see, you ask Ratnathan, will show you. He will do one experiment for banetic transformation. Actually, basically we do banetic transformation in salt bath. Okay, you can ask Ratnathan and he will show you. You understood? So 7 different temperatures, 7 different samples. So you put all the samples in different bath, you austenitize the sample for small interval of time and you take out and quench it. You quench all the samples. Just put it into the water directly. From the salt bath, you take it out and put it into the water. So what is the final microstructure? What is the final microstructure? Can you, from the back side, can you tell me? What is the final microstructure? The moment you take out the sample and put it into the water. From T1 temperature, T2 temperature, T3, T4. Martensite will form? Right, I told you that is the product phase. So gamma will become BCT. And this is due to quenching. Quenching means what? Okay, done. Now, somebody will ask, can you tell me in which, from out of the 7 case studies, in which have maximum transformation happened? That means maximum initial phase, which is 100% perlite, has transformed into austenite. Can you tell me? Listen to the question again. My question is, out of these all 7 samples, out of all these 7 experiments, you can say, in which experiment you got maximum transformation of perlite to austenite phase? Just check it, and we already discussed that earlier. T7, yes. The T7 will be having maximum austenite. So how you will get it? Because austenite cannot remain in the room temperature phase. After quenching, you will get martensite only. Right? You may have some amount of written austenite. I am not going into that. Just imagine you have 100% transformation of austenite into BCT, that is martensite. Okay. So how you can determine? Just check the amount of martensite phase. You will see that T1 temperature experiment have very less amount of martensite, T2 have more, T3 have more, and T7 have a maximum of martensite. Why this is happening? Because you understood that means transformation has happened from perlite to austenite, then austenite to martensite. Like this transformation has happened. So initial is perlite. So you do heating, it will become austenite. Then you do quenching, that is rapid rate of cooling, you will end up with martensite. So in other way, I can say amount of martensite will depend on the amount of austenite, of course. So you can indirectly you can see the amount of martensite, and you can say that in T7 we have maximum martensite. That means we have maximum austenite phase during the phase transformation or during the heat treatment process. Okay. So this experiment you can do that. You can ask her to do this. So you understood That means the phase transformation temperature is important for the what? To study the kinetics. So in other way I can say kinetics of transformation of austenite is faster if the temperature chosen is higher. So higher is the austenitizing temperature or higher is the transformation temperature, kinetics is fast. That means T7 temperature, most of the perlite will transform into austenite quickly. We got the point. Similarly, but condition is what? Holding time is same. You cannot change the holding time. But now the second point is you can change the holding time. You choose this temperature, 77 now, maximum kinetics. So kinetics is maximum in this condition. Higher kinetics. Now you choose, you can modify the holding time, which vary the holding time. You can start with maybe some half an hour, then 1 hour, maybe 1.5, 2 hours, 3 hours. So more is the holding time, what will happen? More is the transformation will happen to the austenite phase. So second point is the holding time also affect the kinetics. So higher is the holding time, higher is the kinetics, you can say. Or in other way I can say more nucleation, more growth will happen if holding time is more. No, obviously because this transformation happened due to nucleation and growth. So more is the holding time, more nucleation, more growth. Similarly, higher is the transformation temperature, higher is the nucleation and higher is the growth. So how I am correlating, you understood? Right? You can write in exam also, in end semester, if the question will be in the end semester, you can write. Again I am saying, higher is the austenitizing temperature or higher is the transformation temperature, higher is the kinetics of the austenite formation. Why? Because nucleation rate is also high, growth rate is also high. Similarly, higher is the holding time at the austenitizing temperature, higher is the kinetics of the austenite transformation. Okay? From this diagram, actually if you remember the diagram, you can write everything. There is no confusion. Just remember this. That's why iron carbon diagram is called heart of metallurgy. People call it like that. Many people call it the heart of metallurgy is iron carbon thing. Because from this diagram you can got a lot of information. It's not a aluminum diagram is also very important for physical, for extractive metallurgy. Similarly, this diagram is very important for physical heat treatment, for everything. Okay. But the question comes is now this one. See, higher carbon steel and lower carbon steel. Okay, to explain that, let me discuss about this. I talk about perlitic colony. You have understood the lamellar spacing also. So your perlitic nature will also decide the kinetics of transformation. Whether you have fine perlite or whether you have coarse perlite or you have more number of cementite, these three things will decide your transformation. Again I am saying, suppose you have fine perlite, it will decide the kinetics. You have coarse perlite, it will decide the kinetics. If you have more number of cementite, then it will decide the kinetics. So question is now, you have high carbon steel and you have low carbon steel. All are plain carbon steel. In which case the kinetics will be faster for formation of austenite. Can you tell me? Low carbon. The last point I talked about is amount of cementite. If more cementite will be available, kinetics will be faster. So high carbon means what? More cementite will form, of course. Higher is the amount of carbon, more is the cementite amount. So thickness of cementite form will be bigger. So interlamellar spacing will be reduced, of course. Interlamellar spacing will reduce now. Higher is the amount of carbon, higher is the amount of cementite. So interlamellar spacing will be less. Because that is the distance between from center of one cementite to another center of one cementite. Okay. So kinetics will be faster in high carbon steel compared to low carbon. And if you want to go to depth, how you can explain? Nucleation and growth. Nucleation starts due to what? Diffusion of carbon from cementite to the interface. So more carbon is available in the cementite, so more diffusion will happen, more nucleation will be there, more growth will be there also. So in depth you can also explain. Similarly, next one, fine and coarse. Now can you tell me? You know that. In between fine perlitic steel and coarse perlitic steel, which have higher kinetics? Fine. Because distance is very less. So diffusion distance will be also very less. See, more is the diffusion distance, more time it will take. So kinetics will be slow. If the diffusion distance will be less, nucleation will be fast, growth will be also fast. So that is the reason I told This kind of phase transformation is based on nucleation and growth. So higher is the nucleation rate, higher is the growth rate, higher is the kinetics. So fine pearlite steel have higher kinetics. It will easily form austenite. Is it fine? Now this is the last point we have discussed in the previous lecture. Can you tell me in which case you have two alloy steel? One is having lot of strong carbide formers, like chromium is there, maybe it contains some vanadium, niobium, tungsten, which form very stable carbides, and the steel which have alloying element which do not form any carbides. So in which case the kinetics is faster, and in which case the kinetics is non-carbide. Very good, non-carbide. Why? What is the reason? Because the reason is, if the carbides are very stable, then the solubility of carbide in austenite is very slow. It will take a lot of time. It may also take high temperature. So listen it carefully. If you are dealing with a alloy steel having carbide forming element, you need to austenitize the sample at a very high temperature. Then only everything will become austenite. Otherwise you will not get a homogeneous austenite phase. Again, shall I tell again? If you are dealing with a alloy steel with carbide forming element, which are very strong carbide former like chromium, tungsten, vanadium, niobium, which are very stable carbides, you need to austenitize the sample at a very high austenitizing temperature. Otherwise those carbides will be not soluble in the austenite. Unless until they will soluble, you will not have a homogeneous austenite phase. That is the parent phase we need. Then only transformation you need. No? Okay. But you might have a question. Sir, already we have these carbides which are precipitates, which can prevent the motion of dislocation. Then why we are doing again, we want to dissolve it, again we want to produce those carbides? You got my question? This is a very tricky question. Listen it carefully. You got a steel, you have those precipitates of carbides. Maybe niobium carbide, tungsten carbide, vanadium carbide, you have already, right? You have pearlite, whatever you want. But still we are doing this kind of heat treatment. We are taking to high temperature, we are making everything austenite. Again we are transforming it, again we are getting same precipitates. Yes. The answer is, we are doing this kind of heat treatment because initial carbides are coarser carbides. But by doing heat treatment, the precipitate you will obtain as very fine out. And that is actually good. That will provide you good strength. You got my point? So because everything we are getting by what? By melting and casting. You are doing melting and you are doing casting. The moment you are doing casting, you are getting same precipitate, but those are very, very big precipitates. You need to give some heat treatment. By doing heat treatment, you can produce very fine carbides. Fine carbides means lot of carbides, lot of interaction between the dislocation and the carbides. Dislocation cannot move easily, and it need to shear it also. That is the shear mechanism. And to do shear, you need more energy. More energy means you need to provide more tensile strength. Obviously, strength will be more. These are the concepts. Okay, we are done now. So these are very important. You need to explain why. In the exam, you need to explain why. If there is a question to compare this, why kinetics is faster, why kinetics is slower. All actually depend upon the interlinear spacing. So diffusion distance is matter. Because nucleation always happens due to diffusion, basically in this case. Growth also happens due to diffusion. I don't know, you have studied this or not. There is two kind of phase transformation. One is called reconstructive, one is called displacive. I don't know, sir, have taught you or not in phase transformation. Okay, you can go through my videos available on the internet. That is heat treatment lecture. It is there. Two type of transformation. One is called reconstructive, one is called displacive. Displacive transformation is the Martin-Cyclic transformation actually. There is some shear will occur, displacement. And reconstructive transformation is pearliting. Reconstruction means everything will break down and again rearrangement will take place. Why? Why? Because BCC structure is one kind of crystal structure. Atoms are arranged in a particular fashion. But the moment you want to form austenite, FCC, so you have a different arrangement? Of course, no. In BCC, 8 number of atoms in the corner and 1 at the body center. But the moment you break down into FCC, so from the body center, atom has to move and it has to arrange in the phase centers. So that means initial bonds will break down and new bonds will form. So that's why it is called reconstructive. So Perlite transformation is always a reconstructive phase transformation. You have to remember. Similarly, again you want to convert austenite into perlite. Again reconstruction will happen. Again the FCC will break down and it will become BCC. So that is called reconstructive. All initial bond will break down and new atom arrangement will take place. But displacive means nothing will break down. They will just shear. So go through those videos. That is very interesting. If you want to do research further, MTech or maybe PhD, it will be helpful for you. Okay. Thank you.